back again. This is Elementary Algebra. I am your instructor, Amy Fuchsteiner. We are currently working on section 8.4 in radical expressions. We've talked about how to multiply and simplify square roots and some cube roots and some higher orders. Today we're going to work on just adding and subtracting when you have radical expressions, and we are going to concentrate on square roots. All right, so we want to talk about what it looks like to be like radicals and what it looks like to be unlike radicals. So like radicals are radicals where you have the same radicand. So the square root of 5 is like the square root of 5. You can add square roots together only if they are the exact same square root. It's like fractions can only be added together if they're the exact same denominator. The same sort of general rule applies here. You can only add together square roots if they have the exact same radicand. Unlike radicals would be like the square root of 5 is not like the square root of 15. These are two different square roots, so they're not like. The square root of 5 is not equal to the square root of 15. We cannot add them together. They are not like radicals, right? So how do we simplify like radicals? In my brain, you doing okay, Ozzy? Yeah, it's just more math. Ozzy is everyone. Okay, so to simplify like radicals, my brain treats them like exponents. Like this very first problem here says the square root of 3 plus 5 square roots of 3. I just think of this as x plus 5x. They're exactly the same. So x plus 5x. Since we're adding them, you want the long way around? You don't, but I'm going to give it to you. The long way around would be to think of this like a 1. Right? And then to do what we have been doing in previous sections, which is to factor out a square root of 3. See that square root of 3 in both of them? Factor it out front, and then you're left with 1 plus 5. Or the square root of 3 times 6, which is 6 square roots of 3. 1 square root of 3 plus 5 square roots of 3 is 6 square roots of 3. Now, when I say it, it's like when I say 1 red fish plus 5 red fishes is 6 red fishes, right? 1 red fish plus 5 blue fish. I can say it's 6 fishes, but I can't specify anymore if they're red or blue. We lose something in that, right? So red fish, 1 fish, 2 fish, red fish, blue fish. So 1 square root of 3 plus 5 square roots of 3 is 6 square roots of 3. If we look at problem number 2, we have a negative 7 square root of x. Is there a like term in here? Yep. Negative 7 square root of x plus 10 square roots of x is 3 square roots of x plus 2 square roots of y. Can I add together square roots of x with square roots of y? Those are not like radicals, right? They're not exactly the same underneath. So this is it. This is as far as I can go. I can add my like ones. Negative 7 plus 10 is 3. Ignoring what's underneath the square root, I've already determined that it's like. And then all I can do is add on what was remaining there with the unlike. Okay? Now, you know it can't be that easy, right? There is a little bit of a sort of hook we can throw in this. And that is that if those square roots are not already simplified, we have a problem. Take, for example, the square root of 12 plus the square root of 27. The square root of 12 can be simplified. So the square root of 12 is 2 times 6, which is 2 times 3. So this is 2 square roots of 3. The square root of 27 is 3 times 9, which is 3 times 3. So this, I can pull a 3 out, is 3 square roots of 3. So what I have here is 2 square roots of 3 plus 3 square roots of 3. Do you see how now they're like? Those are like radicals. So I can add them together. 2 square roots of 3 plus 3 square roots of 3 is 5 square roots of 3. And now I got it. Now I can combine them. It was deceptive because up here they weren't simplified. Once I simplified them, I was able to see that I could add them together. Right? Let's look at number 4. I have 5 square roots of 18 and 2 square roots of 8. The 5 I'm going to leave there. 18 is 9 times 2. So the square root of 9 times the square root of 2 minus 2, and I can break the 8 into the square root of 4 times the square root of 2. So 5 times 3 square root 2 minus 2 times 2 square root 2. Or 15 square roots of 2 minus 4 square roots of 2. 15 minus 4. Do you see how now they're both square roots of 2? So I can combine them, giving us 11 square roots of 2. How did I know I could simplify? Well, there's a couple of clues. First of all, 8 and 18 are both even. They're not perfect squares, but they're also not prime. So when my numbers are not prime, 18, 8, not prime, then I feel like I have to simplify them. Did I have to use this manner to simplify them? No, you could have gone with something like this. I'm just trying to demonstrate both methods again for whichever one works best for you, right? Because we have 2 different ways of doing this, well, simplifying that is, I might want to demonstrate both ways. Okay, problem number 5. The square root of 20 minus 2 square roots of 45 plus the square root of 80. 20 is not a perfect square, but it's also not prime. So I'm going to break 20 into the square root of 4 times the square root of 5, or 2 square roots of 5. Then I have minus 2. The square root of 45 could be broken into the square root of 9 times the square root of 5. Or minus 2 times 3 square roots of 5. And then I have 80. 80 is a hard one. I'm going through my squares. 4 works. But I've got a whole lot left. I want the biggest perfect square that'll go into 80. This would be the square root of 16 times the square root of 5. So plus 4 square roots of 5. So I've got 2 square roots of 5 minus 6 square roots of 5 plus 4 square roots of 5. 2 minus 6 is a negative 4 plus 4. Oh, man. All that work for 0. So I've got negative 4 square root of 5 plus, or if you'd rather, add the 2 and the 4 to get 6 square roots of 5 minus 6 square roots of 5 is going to be a 0. So this guy is 0. All that work for nothing. Yep, welcome. Okay, problem number 7. I have 32x to the 5th minus 218x to the 5th. Oh, I like that. Okay, so 32x to the 5th is going to be the square root of 32 times the square root of x to the 5th. I'm going to do this one first. So that's going to be the square root of 2 times 16, 2 times 8, 2 times 4, 2 times 2. And x to the 5th is going to be x to the 4th times x. So I'm going to be able to pull out 2 2's, or 4 square root of 2 times x squared square root of x. So I've got a 4x squared square root 2x. Oh, I should have gone down. I went over. Oops. Minus 2. 18 is a 2 times 3 times 3 times, and I can do x to the 4th times x again. Okay, so I can pull out a 3. So the 2 stays. I can pull out a 3. Square root of 2 times x squared square root x. So minus 6x squared square root 2x. All right, minus 6x squared square root 2x. So 4x squared square root 2x minus 6x squared. 4x squared minus 6x squared 2x is 2x. So minus 2x squared square root 2x. That one was a little rough. Some of these can get a little bit long, but yep, that worked. Okay, what about number 6? So that's a 2x squared. So that's going to be a square root of 2 times the square root of x squared. So that's going to be an x square root of 2 plus 8 square root of 8 times square root of x squared. So square root of 8 is going to be the square root of 4 times the square root of 2 times the square root of x squared. So x square root of 2, that was the easy one, plus 8 times 2 times square root of 2 times x. Remember, we don't like to have those x's on the end. We want to move them in front of the square root whenever possible. X square root of 2 plus 16x square root of 2. X square root of 2 plus 16x square root of 2 is 17x square root of 2. Why 17? Why 17? Sorry, we're glitching. We're glitching. There we go. We good? Because this is a 1x plus a 16x is going to give me a 17x. These 2's are the same, so I can add them together. Here we go. All right, this last one looks like a little bit of a beast here. Oh, so I'm going to start, and sometimes when they get beastly like this long, I just sort of split them into 2. So this would be 5. 18 is the square root of 9 times the square root of 2 times the square root of a cubed times the square root of b to the 4th. So 5 times 3 times the square root of 2 times the square root of a squared times a. I really should have split that up, times b squared. So 15 square root of 2 times a square root of a times b squared. All of these that are underneath, or not, I'm sorry, all of these that are not underneath this square root, I'm going to pull them all forward. So I'm going to have 15ab squared square root of 2a. And that's as simplified as I can get that one. Now for the other one, I'm going to have a 2 out front. 27 is the square root of 9 times the square root of 3. A to the 5th would be a to the 4th times a times the square root of b squared. So that's going to be 2 times 3 square root 3 times a squared a times b, or 6 square root of 3 times a squared square root of a times b. I'm going to pull all these suckers not underneath the square root out front. I got 6a squared b times the square root of 3a. Minusing them. Can I combine? What's a 15ab squared? That's a 6a squared b. Regardless of what's underneath the square roots, I don't have like terms here. These still need to be like too. So the best I can do is 15ab squared, square root of 2a, minus 6a squared b, square root of 3a. Putting it all together and listing it as is. Simplified, but I can't combine them. Yankees, that was a beast. All right. Some application problems, really just doing the same thing but applied. What is the perimeter of this property that is shown? perimeter is just going to add all sides. So we are going to take 7 times the square root of 54, and we are going to add that to 10 times the square root of 150. And we're going to add that to 13 times the square root of 24. And we're going to add that to 9 times the square root of 96. Okay. In the simplest form, so 7 square root 54 would be 7 times 54, 9 times 6, square root of 9 times square root of 6. So this will be 21 square root 6. 150, that's 25 times 6, or 50 square roots of 6. 24 is 4 times 6. So that's going to be 26 square root 6. Square root of 4 is 2 times 13 is 26. 96. Listen, the only way I can add it is if I end up with the square root of 6. And so while I'm not sure, I'm going to see if 96 is divisible by 6. I did 16 by 6. So this would be 9 times 16 times the square root of 6. And that's going to be square root of 16 is 4 times 9 is 36 square root of 6. All of these will be square roots of 6. 21 plus 50 is 71. Plus 26 is 97. Plus 36 is 127. 6 is 133. So I'm getting 133 square root of 6. So if I do 21 plus 50 plus 26 plus 36. Yep, 133 square root of 6 feet. And that, again, would be the exact answer. Remember when we were working with pi and I talked about the exact answer and the not exact answer? This is the exact measurement. Because if I do anything with the square root of 6, I'm going to end up rounding. And I don't want to round. I wanted the exact measurement, I think. Did we? Oh, it didn't say. It should say. It should say what is the exact perimeter. Right? Because if it didn't say exact perimeter, why did we do all this? Why didn't we just use a calculator and not even worry about simplifying? Because I didn't write the problem out correctly. Right? This should say simplify radicals to find the exact perimeter of the property. Okay. All right. Problem number 10. The height of a bracing pole is determined by the formula H is equal to S square root 2 over 2, where S is the length of a side of the tent. We want to find the height of each pole. So for the parents, the side of the tent is 6 feet. So the height of the pole would be 6 square root of 2 over 2, which 6 over 2 is 3 square roots of 2. For the kids, each side is 4 feet. So the H, or the height of the pole, would be 4 square roots of 2 over 2, which is 2 square roots of 2. Part B says if there are 2 poles needed for each tent, so 2 for the parents, that's 3 square roots of 2, and 2 for the kids, which is 2 square roots of 2. So that's going to be 6 square roots of 2 added to 4 square roots of 2. What is the exact length needed to fabricate the 4 poles? So 2 from the adults and 2 from the kids. 6 square roots of 2 plus 4 square roots of 2, which is 10 square roots of 2, feet. And this one at least said exact. This would be our exact length. Do people need exact length? Yeah, sometimes. Exact length is often used if you have different types of fabricators. Maybe one machine only needs to have it to 1/10 of an inch and another machine needs to have it down to 1 millimeter. So you might need to know it's 10 square roots of 2 rather than what is 10 square roots of 2? 10 square roots of 2 is 14.14213562. And yes, if you are working with aluminum poles, you could probably just figure out that this was 14 feet. What would that be in inches? So to get the inches, I'm going to multiply this by 12, take the feet off. So you would probably be okay if you just cut it to 14 feet 2 inches, that would be enough. But if you're fabricating it on a much more precise manner, you might need to know that it was 14 feet 1.7 inches. So in those cases where there are different fabricators involved in a larger project, they would probably just use 10 square roots of 2 as something that then each fabricator could calculate themselves. Hey, I only need it to, inches. Hey, I need it to inches and millimeters or whatever. So, okay. All right. Excuse me. That's the end of it for 10-4. Not 10-4, 8-4. 10-4, good buddy. 8-4 is now complete. If you have questions on any of this material, please reach out and ask. I am available for help, as is Julia and the Math Center. We all want to see you succeed. We know this is the very end and the final push, and we hope to help you get over this finish line. All right. Thank you, and we'll see you next time. Bye-bye.